Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Albert Einstein's 1907 paper on the influence of gravitation on the propagation of light represents a pivotal step in the development of his theory of general relativity. It stands as a testament to his remarkable ability to synthesize seemingly disparate concepts, forging a path toward a revolutionary understanding of gravity. This work, emerging well before the full articulation of general relativity in 1915, reveals Einstein's early grappling with the implications of his principle of equivalence, a conceptual bridge that would ultimately link gravity and acceleration. The genesis of this paper lies in the intellectual ferment surrounding special relativity, published in 1905. Special relativity had irrevocably altered our conceptions of space and time, demonstrating their interconnectedness and their dependence on the observer's relative motion. However, it conspicuously omitted gravity, a force that Newton's theory had successfully described for centuries, albeit in a manner that Einstein found fundamentally unsatisfactory. Newtonian gravity posited an instantaneous action at a distance, a concept at odds with special relativity's insistence on a finite speed limit, the speed of light, for all interactions. Einstein sought a theory of gravity that was compatible with his newly established principles of relativity. A crucial stepping stone presented itself in the form of what Einstein termed the happiest thought of my life. This was the principle of equivalence, the realization that the effects of gravity are indistinguishable from those of acceleration. Imagine, Einstein proposed, an observer inside a closed box. Should this box be resting on the surface of the Earth, or accelerating upwards in empty space with an acceleration equal to the Earth's gravitational acceleration, the observer, within the box, is unable to perform any experiment that would reveal this distinction. This simple, yet profound, insight provided Einstein with a powerful tool for investigating gravity, namely the ability to analyze it through the lens of accelerated frames of reference. In his 1907 paper, Einstein explored several key consequences of the equivalence principle. A particularly striking prediction, and the central theme of the paper, involved the bending of light by gravity. Einstein reasoned that if gravity and acceleration are equivalent, then light, which exhibits inertia, is similarly influenced by gravity. This influence manifests as a bending of light rays as they pass near massive objects. To understand this, consider the accelerating box once again. A light beam entering one side of the box travels in a straight line relative to an inertial observer outside the box. However, to the observer inside the accelerating box, the light beam appears to curve downwards, as the box moves upwards during the time the light is traversing it. By the equivalence principle, the same phenomenon must occur in a gravitational field. Einstein calculated the angle of deflection of a light ray passing near the Sun. His initial calculation, based on an incomplete theory, yielded a value that was half of the value predicted by the full theory of general relativity in 1915. It is crucial to note that Einstein's 1907 calculation contained a subtle error stemming from his approximate treatment of the gravitational field. This highlights the complex interplay between intuition and rigorous calculation in theoretical physics. Even brilliant insights require careful mathematical execution. Another significant prediction of the 1907 paper concerned the gravitational redshift. Einstein argued that clocks run slower in regions of stronger gravitational potential. This phenomenon, known as gravitational time dilation, arises directly from the equivalence principle. Imagine two observers, one at the top of a tower and the other at the bottom. The observer at the top of the tower is in a region of weaker gravitational potential than the observer at the bottom. If the observer at the top emits a light signal of a specific frequency towards the bottom, the observer at the bottom will detect a slightly higher frequency, shifted towards the blue end of the spectrum. Conversely, a signal emitted upwards will be redshifted, that is, shifted to a lower frequency. This implies that time elapses differently in regions of different gravitational potential. The frequency shift, or equivalently the time dilation, is proportional to the difference in gravitational potential between the two locations, divided by the speed of light. Mathematically, Einstein expressed the relationship for the change in frequency delta nu to the original frequency nu as equal to the change in gravitational potential phi, divided by the speed of light c, all squared. In equation form, this expresses as delta nu over nu equals delta phi over c squared. This prediction of gravitational redshift offered, at least in principle, a testable consequence of the equivalence principle. The immediate impact of Einstein's 1907 paper was modest. It appeared in the Jahresbericht der Radioaktivität und Elektronik, a journal perhaps not at the forefront of theoretical physics at the time. Its significance rested more in its role as a crucial stepping stone towards general relativity, than in any immediate wave of experimental verification. The experimental verification of gravitational redshift, in particular, proved challenging. The predicted frequency shifts were exceptionally small, rendering them difficult to disentangle from other effects. Early attempts at verification, such as those by Walter Sidney Adams at the Mount Wilson Observatory, yielded ambiguous results, plagued by observational uncertainties. Despite these initial challenges, the 1907 paper profoundly influenced the subsequent development of general relativity. It laid out the fundamental concepts and physical intuitions that guided Einstein's later work. It established the principle of equivalence as a cornerstone of his approach to gravity, and it highlighted the importance of considering the effects of gravity on light. Furthermore, it served as a catalyst for other physicists to engage with the problem of reconciling gravity with special relativity. One individual directly influenced by Einstein's early work was Hermann Minkowski. Minkowski, Einstein's former mathematics professor, reformulated special relativity in a four-dimensional geometric framework, introducing the concept of spacetime. Although initially skeptical of Einstein's special relativity, Minkowski came to appreciate its profound implications, and his reformulation provided a crucial mathematical language for the development of general relativity. Einstein initially regarded Minkowski's approach as superfluous mathematics, but he eventually recognized its power and adopted it as the foundation for his own work on general relativity. Einstein's 1907 paper also influenced the work of Max von Laue, who explored the implications of special relativity for electromagnetism and optics. Laue's work, in turn, contributed to a deeper understanding of the interaction between light and matter. The paper planted the seed for future generations of physicists to explore the intricate interplay between gravity, light, and space-time. The subsequent evolution of Einstein's work on gravitation, culminating in the full theory of general relativity in 1915, built directly upon the foundation laid in the 1907 paper. General relativity presented a radical departure from Newtonian gravity, describing gravity not as a force, but as a manifestation of the curvature of spacetime, caused by mass and energy. Einstein's field equations, a set of 10 coupled nonlinear partial differential equations, elegantly express this relationship. These equations relate the curvature of spacetime, represented by the Einstein tensor, to the distribution of mass and energy, represented by the stress-energy tensor. Solving these equations, even in simplified scenarios, presents a formidable mathematical challenge. The bending of light, initially predicted in the 1907 paper, received a more accurate and complete treatment within the framework of general relativity. Einstein's 1915 theory predicted a deflection angle twice as large as his earlier estimate. This prediction gained dramatic confirmation during the solar eclipse of 1919, observed by Arthur Eddington and his team. The measured deflection of starlight passing near the Sun agreed remarkably well with Einstein's prediction, catapulting him to international fame and solidifying the acceptance of general relativity within the scientific community. The gravitational redshift, also anticipated in the 1907 paper, found experimental verification several decades later, with increasingly precise measurements. The Pound-Rupke experiment in 1959, which utilized the Mossbar effect to measure the minute frequency shift of gamma rays traveling vertically within the Jefferson Physical Laboratory at Harvard University, provided a crucial confirmation of this prediction. Subsequent experiments, employing atomic clocks flown on rockets and satellites, offered even more precise measurements, further validating the predictions of general relativity. While the 1907 paper was a groundbreaking contribution, it did face certain critiques. Some physicists questioned the validity of extrapolating the equivalence principle to arbitrarily strong gravitational fields. The principle, after all, was initially conceived in the context of uniform acceleration. Others raised concerns about the lack of a complete and consistent mathematical framework for describing gravity within the context of special relativity. Einstein himself recognized these limitations, devoted the subsequent years to developing the full theory of general relativity to address these concerns. It is fair to conclude that the influence of gravitation on the propagation of light occupies a unique and important position in the history of physics. It represents Einstein's early, insightful grappling with the problem of gravity, laying the conceptual groundwork for his later masterpiece. It highlights his remarkable ability to connect seemingly disparate concepts, forging a path toward a deeper understanding of the universe. While the paper's immediate impact may have been modest, its lasting legacy is undeniable. It served as a crucial stepping stone towards general relativity, a theory that has revolutionized our understanding of gravity, spacetime, and the cosmos. The paper's predictions, initially tentative and approximate, have been confirmed with increasing precision, solidifying its place as a seminal work in the history of physics.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.